Hello, everyone. Welcome back to Codex. Our talks this summer will feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today, we have Sawyer Robertson, who is a graduate student at UC San Diego. We are happy to have him here today to tell us about effective resistance and conductance for probability measures on graphs. Take it away, Sawyer.
Thank you, Mike. Yeah, I'm really happy to be here today to be sharing some of the things I've been thinking about in the past couple of years with you all. The My talk today is going to concern some data science problems on graphs, some optimization problems defined for regions on graphs, and yeah, I hope it'll be enriching for everybody. So let's just jump right in. So. Uh, let's see. There we go. As a bit of an appetizer, I want to talk about a few toy examples of what I'm going to call graph-based data science problems or data science problems that involve graphs. And all of these examples are things that have kind of emerged, particularly in my research, but as instances of sort of broader methods, broader problems as well. So the first example, is something that if you're familiar with like the graph neural network literature or much of the graph-based data science literature, you've probably heard of citation networks. Citation networks are constructed from vertex sets that consist of papers, right? So papers on a particular topic or papers in a field. In this case, I'm showing you what's known as the Cora data set. It contains a bunch of computer science papers and these papers are connected with edges in a network if one paper cites another. So it's a very kind of natural relationship, or maybe I would use the word intrinsic relationship that exists on a set of research papers in a field. And a common task that is sometimes opposed with a data set, with a graph like this, is to try and predict the topic of a paper, right? Maybe by only labeling a few of them and then trying to design some sort of classification model. So another instance of a graph that appears in maybe a data science problem is that I wanted to mention is a geometric graph. So in this case, I've designed a geometric graph by taking a section of grid points in latitude longitude space on the sphere, and we've connected them based on proximity in Euclidean space. And so this particular graph was used in a weather pattern modeling problem. And what you're looking at here are some vector fields that were derived from hurricane trajectories. There's a really awesome hurricane trajectory data set that we used to construct these vector fields in a meteorology problem. Like I said, this is another example of how a graph might emerge or be used, maybe even sort of artificially in a data science problem. Another example here is a graph that was built from a digits data set. So the data set that's sort of underlying this image you have in front of you is the sklearn digits data set. If you're familiar with MNIST, it's like a slightly smaller scale version of MNIST. It consists of approximately 2,000 grayscale images of handwritten digits in the resolution 8 by 8, so pretty small. And so these edges that I've constructed in this graph are just based on Euclidean proximity in that 64-dimensional feature space. So with this graph, we can also try to approach, let's say, like a classification problem or something like that, maybe where we want to try and predict what the class is of a particular digit that you've been handed. And we'll actually, at the end of the talk, we'll return to this specific figure and I'll add a little bit more context to what's going on and how it was used. So having said that, giving you a bit of an appetizer for graph-based methods in data science, the setting of this particular talk is going to be what I'm going to call two worlds within this field. So the first world is optimal transportation on graphs. Loosely speaking, maybe insultingly loosely speaking, this refers to a family of optimization problems on the probability simplex of the vertices of a graph. I'll elaborate on that momentarily. And the second world that I'm going to talk about is graph-based semi-supervised learning, which concerns methods for building data classification models in label-sparse regimes. And these methods are built upon constructions of what I'll call sort of well-designed graphs. And the idea or let's say the goal of this particular talk is to convince the listeners, to convince you all of what I feel some surprising duality between these two worlds. I'm not going to convince you that they're the same worlds because they're not, but actually there's a nice looking glass effect that if posed correctly, you can think of these two problems, these two families of problems, let's say, as having some duality. And we'll also kind of in the process, we'll cover some new work and some results in each of these individual spaces along the way. So let's start by talking about optimal transportation on graphs. That'll probably be maybe like a slight majority of the talk itself will be optimal transport and some new ways that we are thinking about it in the past couple of years. So first, I'm going to introduce a little bit of notation. I'm going to try and keep the notation light for most of the talk, but let's just agree on some general language for how we'll refer to graphs and work with them. So when I talk about a graph, I'm talking about a weighted, connected, undirected graph, and I'll use the integer n for the number of vertices and the integer m for the number of edges going forward. These weights, by the way, W, these are symmetric weights, right? So they're just defined on these undirected edges, and they are by convention positive. So the probability simplex on the vertex set of the graph is just a set of functions, real valued functions on the vertices, which are non-negative and which have a unit sum. I'm also going to use this metric dij. This is the weighted shortest path metric between two vertices, in this case, ij in the vertex set. And a small kind of abusive notation note, I'm going to identify functions on the vertex set and vectors in Rn. And also, since our graph is finite, probability measures and density vectors, I'm going to sort of use that terminology, even if I'm running the risk of being a bit abusive, I'm going to use it interchangeably. So in particular, in the former case, we'll assume the vertices are enumerated somehow from 1 to n, and having made that enumeration, we can just really speak interchangeably about vectors and functions here. So I'll be doing some linear algebra with functions. Okay, so having said that, so generically speaking, optimal transportation concerns, a variety of optimization problems, which model how costly it is to move mass, which is given by probability distributions in a graph, from one location, mu, to another location, nu, in a metric space. So in this case, I'm using mu and nu as my reference probability measures. And in particular, you can think of an image like this in the graph setting in particular, where I have some ambient graph. In this case, it's sort of a hexagonal lattice. And I have a measure mu here that's denoted with a few blue nodes and a measure nu that's denoted over here with red nodes. And the idea is of all of the ways that I can assign, let's say I'll use the term flow, of all the ways that I can assign a flow to the edges, which would allow me to move the mass at mu to the mass at nu. Optimal transport gives me a formal framework through which I can understand the optimal way to do so. So I'll be a bit more precise in the next slide. So first, I'm going to define the set of couplings. So the set of couplings between a pair of probability measures will be the set, in this case, of matrices, which are non-negative and which have, let's see here, row sums equal to mu and column sums equal to nu. And actually, column sums equal to mu and row sums equal to nu. That always confuses me. And visually, there's a cartoon you often see when the notion of a coupling is defined, at least in the discrete space, which is that in some sense pi here is a matrix, and if you sort of view it from one direction, in this case looking up, you're going to see mu, and if you view it looking left, you'll see nu. So you can also think about mu. It's a little bit of arithmetic. You'll see, pi. It is a probability measure on the product of the vertex set, and its marginals are going to be mu and nu respectively. So Wasserstein distance in this setting can be defined as an infimum of a penalty function here, pi ij times the distance from I to j over all of the vertices ij in the vertex set. In this case, I'm raising dij to the p, where p is some number between 1 and infinity. This infimum here defines a metric on the probability simplex. So this allows us a way to capture the distance, let's say, between mu and nu. This is, I'm defining it here in the graph setting because I don't want to bite off more than we have to chew. But of course, this can be defined really in any metric space. And there's a lot of robust theory that has been written about that particular topic. So in the setting of graphs, it is interesting to note that when p is equal to 1, W1 can be recast as what is known as a minimum cost flow problem. So specifically, this program is defined as an infimum of a weighted L1 norm over all vectors on the edges, which satisfy a constraint, a linear constraint, bj equals mu minus nu. And in this case, the matrix B is the oriented graph vertex edge incidence matrix, which explicitly, if you want kind of an entry-wise definition, looks like this. It's basically kind of highlighting incidence between an edge and a vertex in an oriented manner. So the word oriented here refers to fixing an orientation on the edges. It's kind of like artificially or virtually putting a direction on your graph so as to have kind of a consistent definition. However, that direction is in most cases kind of artificial. And if you want to think about its action on this vector j, I will refer to these vectors, by the way, as flows. If you want to think about its action on a flow, you can think about bj at a node I as basically the difference between the outgoing mass at a node minus the incoming mass. So it's sort of measuring a displacement or a divergence, if you prefer that term, at a particular vertex. So if this particular result, when I say result here, I'm referring to the ability to recast W1 as a min-cost flow problem. This can be shown by computing Lagrangian duals of the programs repeatedly. So if you start with W1, compute a dual, compute another dual, you'll land on this particular program. Okay, so this problem has sometimes been called, I certainly call it, the Beckman problem on graphs. Beckman here refers to Martin Beckman, who worked on some optimal transport problems on Rn. And the sort of, the word escapes me, the sort of a visual resemblance between this flow-based optimal transportation problem and the problems that Beckman worked on in the 50s led to kind of adopting the terminology Beckman problem in the graph setting in recent years. So, I mean, this particular program has lots of applications. One I'll highlight is Ricci curvature on graphs. There's been a lot of papers that have used W1 on graphs to formulate a notion of curvature in that setting and have applied it to, unsupervised learning, for example, and clustering methods. I already mentioned the kind of a brief plug about weather pattern modeling. It's also been used in some computer graphics programs. So one of the challenges of implementing this particular program at scale is that J is non-unique. This is, pretty common when you have like a constrained L1 norm optimization problem. A lot of the minimizers there are non-unique, and that is the case here. This uniqueness issue can be addressed via regularization, but even the regularization still leads to this program can be expensive to solve at scale. And when I use the word scale here, I mean it in two ways. Either when the graph itself is very large, or if the number of measures whose pairwise distance you want to compute is large as well. So in those two scaling senses, this can be quite expensive to implement. So with these two challenges in mind, one question that we were thinking about maybe 2 years ago was, what if we focus on the minimum cost flow program to investigate new ways of modeling transport on graphs? So if what we're really interested is transportation on graphs, maybe this minimum cost flow program could be an entry point to some sort of development of different methods or new methods for doing so. So within this kind of motivating question, enter effective resistance. So effective resistance, which is kind of the next topic in our discussion of optimal transport, can be defined as follows. So initially, sort of on its own, it is considered or defined as a metric on the vertices of a graph. So given two vertices I, J, and V, the effective resistance between them is defined via this quadratic form. So what I do is I take the difference between the Dirac masses at I and J, and I plug it into the quadratic form of the pseudo-inverse, the more Penrose inverse of the graph Laplacian, D minus A. So the graph Laplacian here is the combinatorial graph Laplacian. A is like a weighted adjacency matrix. It's just a matrix of the edge weights. And D is a diagonal degree matrix where you add up those edge weights at every vertex. So this combinatorial Laplacian matrix is singular. It has a kernel for a connected graph. Let's say it has a one-dimensional kernel. And so the pseudo-inverse is used in place of the inverse. This metric has a family, a menu, let's say, of different ways that one can formulate it. So a simple sort of recasting of this formula would look like minus pseudo-inverse over 2. So this is going to be a positive semi-definite matrix. It admits a square root, so just take the square root of that. And think about it as being a squared Euclidean distance between embeddings of each node, if you want to think about it that way. If you want to think about this as an embedding of node J, an embedding of node I, that's one way to recast it. Another way to recast it is, you guessed it, a minimum cost flow problem, but in this case with a quadratic penalty, which should be compared to the L1 penalty we saw a few moments ago. This is another way of recasting the problem. And I just put an ellipsis here to indicate that the list goes on. So there's a lot of ways to recast effective resistance. Cataloging all of those would be material, let's say, for another discussion. But there's lots of them, and it's a very a multifaceted metric. Let me put it that way. So this particular metric on the graph originated from electrical network models as the resistance in a network between two unit sources. So if you're familiar with Kirchhoff's law and and you've done some electrical engineering, you might have encountered effective resistance before, and the terminology and the notion in the graph theory context originated from that. And it has deep connections, among other things, to one example I'm going to pick on here is the simple random walk on a graph. So you can write effective resistance as up to a normalizing constant equal to the commute time between two vertices. And the commute time is the expected time to go from I to j and back. So it's a pretty deep connection to the simple random walk, and there's a lot of good theory there. In terms of the applications, this has been applied to graph sparsification, in particular edge sparsification of graphs. That's probably, in my opinion, it's most heavily cited modern application of effective resistance, as well as to graph neural networks and the theory of graph neural networks and how they behave. So one, kind of thought here, random thought, is why don't we just extend this to probability measures? So in principle, we do have a minimum cost flow formulation of effective resistance. It's using a quadratic penalty. And over here, we have that the divergence constraint is that it's equal to the Dirac at I minus the Dirac at j. So why not just extend this to probability measures? And we can try to do that. So let's give that a try. We can take two measures, mu and nu, in the probability simplex, and we can introduce what's known as the P-Beckmann metric, which is given by this family of programs, where I am in essence just allowing that divergence constraint, just like we saw in the W1 formulation, to realize to include the difference of probability measures. And the penalties now are just sort of weighted p norm penalties, right? But for p between 1 and infinity, we just use a standard weighted p norm, and then for p equals infinity, we use a weighted infinity norm. And one thing that I'll note here, just as a notation comment, is that I'm going to put the weight here as a subscript of the Beckmann metric, and that will be important in results I'm about to state, as well as results I state later. So I want you to think about this W as being corresponding to essentially, in particular, power. So W to the 1 would correspond to W to the 1 in the objective. So having said that, one result we can state, which is quite nice, is that in essence, when P is equal to 1, you can recast this program as a optimal transportation metric, a particular Wasserstein metric. When P is equal to 2, you recover effective resistance. Now, you'll note here there is some caution that needs to be exercised regarding the weights. So in particular, when P is equal to 1, the Beckmann metric with reciprocals of the weights recovers the Wasserstein metric with the shortest path distance on the reciprocally weighted graph. And similarly, when P is equal to 2, in order to recover that true pseudo-inverse of the regular weighted graph, you need to weight the quadratic penalty in the Beckmann problem with the reciprocals of the weight. So there's some caution that needs to be exercised with the role that the weights play in the optimization problems. However, we do see kind of a nice sort of an interpolation, let's say, of Wasserstein distance and effective resistance on the probability simplex. Yeah, so this is something that we encountered. If you think of as weights as affinities in this setting, by affinities are sort of inverse distances, let's say, where the affinity is large if the points are close in some sense, and the affinity is small if the points are far away in some sense. If you think of these as affinities, then in some sense, d tilde can be thought of as arguably a more natural distance that when compared to d, in your weighted graph, right? That's one way you might think about d tilde here when accounting for the subtleties with the weights in this statement. So Beckmann 2, or what I'll call measure effective resistance, can be thought of, as a quadratic min cost flow problem for probability measures. And having said that, the picture I showed you earlier, where I illustrated an optimal flow for the L1 problem, for the one Wasserstein problem, now I'm showing you an optimal flow for the Beckman 2 problem, right? So the quadratic min cost flow problem. I've illustrated the flow with the intensity of the colors proportional to the value of the flow on that edge. And as you can see here, as is typical with quadratic programs, the optimal solutions tend to be much less sparse when compared to the solutions to the L1 programs. And but we do also sort of see some amount of concentration of mass on the region where mu and nu, let's say, are most supported, or on the shortest paths between mu and nu. However, as is typical with effective resistance, as is typical, like I said, with quadratic programs, we do see some support on edges that are even far away from mu and nu. So this allows us to kind of understand visually a little bit of the difference between the solutions you get to the Beckman 2 program as opposed to, let's say, the Beckman 1 program. So now I'm going to talk a little bit about some theory for this particular family of metrics, and then after that I'll talk a little bit about some applications of the Beckman metrics. So in terms of theory, one kind of nice result that I'll talk about is that we can essentially recast this optimization program through kind of like in a geometric way as follows. So first, I'll define what I'm going to call the graph Sobolev semi-norm. So for a function f here on the vertices of a graph, I'm going to define the h dot 1 norm of f squared according to this, it's like an L2 norm of its gradient. Let's put it that way. So I'm going to look at every edge in the graph, measure the displacement of the function on the endpoints, square it, and then add that up. That's going to define a semi-norm on the graph, which is a semi-norm because it's not definite on constant functions. So it sort of vanishes in the constant functions. It admits a dual semi-norm, dual or semi, I guess, in this case, in the sense that it's occasionally infinity. But the h dot minus 1 norm in this case would just be defined in the dual sense. And this can be related to the pseudo inverse of the graph Laplacian as well. So we can obtain a version of the Binemo-Bernoulli formula for this particular Beckman 2 metric, which is somewhat nice. So we can recast Beckman 2, or measure effective resistance, as an infimum over these length functionals for curves which begin at mu, end at nu, and are C1. So this is another way to sort of recast and think about this program on the probability simplex. This Beckman 2, this measure effective resistance, also has connections to the random walk on the graph. These require a little bit too much machinery for me to get into in this talk, given the goals of this talk. But is also interesting to note. I will put a plug here that there are connections to the random walk as well. So this setup, everything I've sort of kind of walked through so far, leads to what I would consider to be a natural pipeline for comparatively scalable graph-based unsupervised learning. So the idea is that I'm going to use the digits example when I describe this pipeline. So the idea is that if I start with some kind of, let's say raw feature vector of a digit image, which just lies in the space R64. So this is just an 8x8 image of pixel intensities. The raw data, like if you literally just pull it up on sklearn, the raw data has pixel values between 0 and 15. And so if we just think about this as a raw vector, if you apply a sum normalization to this, you get a probability measure. And additionally, if you think about these pixels as vertices on the 8x8 grid graph, not only do you get a probability measure, but you get a probability measure on a graph. And so in this manner, you can think about taking a raw feature of an image and converting it into a measure on a graph. Moreover, if in this setting you apply the pseudo inverse of the graph Laplacian to the measure, you get a vector in L2 of V, which can have positive and negative values. It will typically be mean 0. Through this embedding, that looks a little bit like this. So you get a little bit of smoothing of the features on the in the vertex space. After doing so, in this L2 space, according to this embedding, after applying this embedding, I should say, the Euclidean distance in this space will recover the Beckman 2 distance. It will recover that quadratic min cost flow optimal transport distance between the measures. So in this pipeline, which in some senses, I mean, technically this step is nonlinear, but it's very easy to implement, very fast. And this is, if you've taken, let's say a SVD of your Laplacian or something, this is also pretty fast to implement. Through this pipeline, you can compute pairwise distances between lots of measures, right? It behaves particularly well when the ambient graph is fixed and the number of measures is quite large. It's quite easy to quickly compute pairwise distances here in this optimal transport metric. And you can draw some comparisons. We can do this empirically. I'm going to do it visually for the purposes of this talk. You can draw some comparisons between, let's say, graphs that have been built. So this is a graph that's built on a graph, right? So I've taken all of these images. I've identified them as nodes in a graph. And using a kernel matrix that I've obtained from this, I have built a nearest neighbors graph here. And so these nearest neighbors graphs that you get through essentially applying standard, off-the-shelf unsupervised methods to a kernel matrix from the Beckman metric tend to be quite, performant when placed alongside more expensive metrics like Wasserstein 2 is the comparison here. Okay, so this is all great. I buried the lead a little bit. I'm going to talk about a result I mentioned a few slides ago. So a few slides ago, I said, I talked about this. I talked about, okay, this family of metrics, the P Beckman metrics. When P is 1, it recovers Wasserstein 1, as long as you're careful about the weights. When P is 2, it recovers effective resistance, as long as you're careful about the weights, okay? This is all well and good. I will share a personal note, which is that when thinking about this, was really consumed with, well, what's happening when P is infinity? I think that's a really obvious omission. And when I say I buried the lead, that's what I mean. What is happening when P is infinity? And it turns out we can say something quite nice about what's happening when P is equal to infinity. It requires a little bit more machinery from optimization to get there, but hopefully not too much for everybody. So we'll go into that now. And we'll talk about what's happening when P is equal to infinity. So usually when somebody mentions duality in optimization context, they're referring to the Lagrangian dual problem, which is formed by, you take your optimization problem, you write down your Lagrangian dual, by incorporating the constraints and some multipliers, and then you find a very good reason to exchange your sup and your env, and then what you get in the process is what's known as the dual problem, right? So instead of a minimization problem, let's say you'll have a maximization problem. And I'm being a little bit light with the details because I'm not actually going to be talking as much about Lagrangian duality in this talk. But what I want to emphasize is that when people talk about strong duality in this setting, they're usually referring to the primal and dual problems achieving the same optimal value. So that's kind of the idea, is that in the Lagrangian dual setting, strong duality means you can have equality of these two things. And I've already used this. I've already mentioned this once in the talk when talking about recasting the coupling formulation of optimal transport to a min-cost flow. It appears in those arguments. However, there is another notion of duality in an optimization context, which is relevant here, and that's going to help us make sense of these Beckman metrics that I introduced in the previous slides. So gauge optimization, generally speaking, refers to programs whose objectives are gauge functions. And these specifically are non-negative functions that are positively homogeneous and that vanish at the origin. They include, for example, minimum norm problems, right? And in general, we are interested in these programs where the feasibility region is some closed convex region of Rn. So gauge duality, to contrast with Lagrangian duality, in this setting refers to transforming a primal problem by replacing the objective with its polar gauge function and its constraint set with its antipolar. And the details here are a little bit technical, but I'll give them to you. So when defining the polar gauge function, one way that you can interpret this is it is essentially the function which best satisfies the Cauchy-Schwarz inequality for the inner product on Rn. So, for example, if you have a norm, a constrained norm minimization problem, the gauge function, the polar of the gauge function is its dual norm, right? So the duality there is kind of what we're familiar with. And then the antipolar for the convex set is given by this description, and it's important to emphasize it's distinct from the polar of the convex set, but it is similarly defined. So having said that, we have a way to talk about a primal problem. Up here, we can obtain its dual problem by defining it like this. And in this setting, strong duality refers to not equality of the optimal values of the primal and dual problems, but reciprocality. So these programs satisfy reciprocality in their optimal values as long as strong duality holds. In this setting, strong duality will hold because our functions our objective functions and our constraint sets are quite well behaved. Okay, so Having said that, having given you a bit of optimization background, I'm going to ask you to consider the following program. So for two distributions, mu and nu, I would like you to consider this program CP of mu and nu, which is given by the minimum over all phi here. So these are vectors in Rn, which satisfy this like affine constraint, right? So I'm looking for vectors phi which have positive inner product against the difference of mu and nu. And the objective function here is going to be reminiscent of what I called earlier. I called this an h dot one semi-norm. You can also just think about this as maybe if you're familiar with, the theory of P-Laplacians on graphs, this is the quadratic form against the P-Laplacian operator on the graph. You can also just think about this as a little bit like an energy functional, right? A P energy functional of the vector phi. So it's not perhaps the most intuitive program at first. It doesn't really necessarily have a lot of easy geometric intuition that comes along with it. But in principle, it makes sense, right? So I'm just looking at all of these, let's call them potential vectors phi that, let's say project positively onto mu minus nu. And I want the one that has the lowest energy in some sense. That's kind of the takeaway, at least at first. And there is a usual modification when P is infinity. I'm going to replace this weighted P norm with a maximum over all the edges of the pairwise difference of the potential. So I'm going to say that this defines the P conductance between mu and nu. And the term P conductance is used since the CP program is the gauge dual to the Beckmann formulation, which is quite nice. So there is a primal dual relationship between all of these Beckmann metrics I introduced earlier and the conductance program, CP. And thus, the reciprocality sort of motivates the terminology, right? Because if you're familiar, again, with the electrical network theory on graphs, you may recall resistance and conductance are reciprocals of each other. And so that's kind of why we use the terminology P conductance for this program. And in this setting, yeah, I mean, up to some modifications on the weights that you should keep an eye on. The CP program is gauge dual to the BQ program, where P and Q are conjugates. If your graph, I want to emphasize briefly that if your graph is unweighted, if you're just dealing with a combinatorial graph, then you can disregard these weights. They're always going to just reduce to 1. So this is a nice result. It is worth noting that, so this extends an existing result of Alamgir and von Luxburg, which considers the case of vertices. So there is an analogous result that just looks at metrics on the vertex side of the graph. And so this work allows us to extend that to the probability simplex and talk about it in terms of transportation metrics between probability measures. Okay. So the program CP is more than just an artifact of a proof, right? So one perspective is just, well, if you just sort of set up the gauge dual, then you get this out of it. But there's something I want to emphasize, which is that setting up the gauge dual doesn't necessarily just reveal everything about what this program can do or what it's telling you about mu and nu. So one theoretical point I'll just mention here is that the case of P equals 1 in particular can be connected to the minimum cuts between probability measures on a graph. So you might recall the like vertex min cut program, let's say, from computer science class. It asks, given two vertices, I and j in your network, how many edges do you need to remove until you have completely separated them, right? And in the case of P equals to 1, this program CP allows us to, in essence, extend that vertex min cut program to a probability measure min cut program, right? Where instead of completely, let's say, isolating the probability measures, you want to isolate them without maybe throwing away too much weight. Let's just put it that way. So there's a way to kind of relax the vertex min cut program that recovers that. But on the applied side, where I'm going to spend a little bit more, invest a little bit more detail, this P conductance program led to a novel graph-based semi-supervised learning method. So now I'm going to talk about kind of the data science side of this particular optimization program. So in semi-supervised learning, we are tasked with building a classification model from a large data set of examples of which only a small fraction are labeled. So that's the idea, is that in typical unsupervised learning scenario, you have sort of, let's say, no labels, and then in the supervised setting, you have a lot of labeled data. And you use that to train a model, right? And then maybe test it on a small amount that you have set aside, or that you have in a use case. In the semi-supervised setting, it's thought of as sort of a midpoint in the sense that I have a large data set, I have a lot of data, and it is in principle labeled. I'm trying to fit a response, but only maybe a 1% of them, let's say only 1% of my examples carry high quality labels at training time. So this is, in principle, it's a quite difficult problem. Graph-based methods seek to leverage the unlabeled examples. So if you have a data set of a billion images or a billion examples, we're going to use the presence of that large ambient data set to inform the model and to build a more accurate classifier by using the structure of the data set, using the geometric properties of that sort of ambient data set that for which the labels, let's say, are latent, but the data themselves are not, to inform a classification model. In particular, in the graph-based setting, we're building a graph. That's how we're doing it. We're going to use a graph, a construction of a graph on that data to inform the classification model later. So to be a little bit more precise about that, I want to emphasize that in this pipeline, in this framework, the training and the unlabeled data points, so including the labeled ones, the unlabeled ones, all of your data at hand, each data point is identified as a vertex in a graph. And the vertices, the examples here, are going to be connected with affinity-weighted edges when the data points are close in some metric. So I'm going to leave the sum metric up to you, up to the data scientist. There's lots of ways to do it. One common way, particularly for high dimensional features, is to, let's say, train some autoencoder or train some neural network that compresses your data with minimal loss into a lower feature space. And then maybe you just want to use Euclidean distance or the Gaussian kernel applied to Euclidean distance after taking the output of an autoencoder. So one of the earliest such methods that is a very relevant tool that is worth mentioning here is Laplace learning. And Laplace learning originated in this paper. I have it cited down here for your reference in 2003, so that's a little bit over 20 years ago. And the idea behind Laplace learning in the binary setting, so to keep things simple, I'm going to talk about the binary class setting, is to take an indicator vector, a -1, +1 indicator vector of the training node labels. So I have the ambient vertex set that contains all of my data, of which a subset T consists of our labeled examples, of which is it's a small proportion. And the idea is that this -1, +1 indicator vector can be extended to the rest of the graph by looking at the minimum of this program here. And so we have this familiar quantity here where I look at potentials phi that have a minimum in this sort of quadratic energy functional over phi whose restrictions to the training nodes agree with the labels, the training labels f. So I'm just trying to take this limited amount of information and extend it in a way that has minimal, let's say, quadratic energy, or if you want to use the h.1 terminology, minimum h.1 norm. And you can then obtain class predictions from this minimizer, f tilde, by just looking at its sign. So on the original set, it's going to agree completely with your training data. And then as you sort of get beyond your original set and into the rest of the graph, you will witness, how do I put this? You will witness sort of a smooth interpolation of your training labels. And this particular program, as I've mentioned a few times, throughout, it can be related quite precisely to the random walk on the graph. If you'd like to think about it this way, you could say, okay, what if you take a node that is unlabeled, so just a generic node for whose class information you'd like to learn, start a random walk at that node, let it run through the graph until it hits a boundary point, which was labeled initially at training time, and then you could record that. If you repeat this process in expectation, you will recover the same prediction as in the Laplace learning pipeline. So it's very related to the random walk. When mentioning the Laplace learning method in 2025, now that we have 20 years of literature and 20 years of methods, it's important to mention that this method does have well-known failure points. And in particular, this method performs well when the amount of labeled data is sufficiently large. So it does perform well with a small amount of labeled data, but when that labeled data at training time starts to, become vanishingly small relative to the total number of examples in your data set, then this method tends to underperform significantly compared to more modern methods because of what's sometimes called like the spike phenomenon, right? It sort of has +1 at the single example you have, and then everywhere else it's just 0, right? Or very close to 0. So there's been a lot of methods in the last 22 years that have sought to address the sort of failure points of this particular method, improve its robustness in the very low labeled data regime. So the program I introduced earlier, the p-conductance program, can be used to define a semi-supervised learning method as follows. So once again, I'm going to assume we're in this binary setting where I have two classes, and I'm going to model the training labels of one class using a measure mu. So we can do that via sum normalization. And I'm going to model the labels of another class, a second class, using a measure nu. So once again, you can use like sum normalization of an indicator vector. So I have a measure of the training examples on one class, and I have a measure indicating the training examples on a second class. I have two measures. And then I can look at a similar program. I'll use the same notation. In fact, I'll recycle it, f tilde, as the argmin over the program here, which looks at a p-norm minimization problem. In particular, p equals 2 would recover exactly the same objective. Modulo weights, there should be a wij here, it's just a little typo. P equals 2 recovers the same objective in the program. However, the constraint is a little bit different. Instead of having a constraint which seeks to like really just extend the original labeled data through just like an extension to the rest of the graph, I'm going to look at a weaker penalty where I kind of have this affine constraint where the inner product of phi against mu minus nu is equal to 1. In this setting, you can think about the vector phi, as I mentioned earlier, as, so I'm just going to sort of wave my hands here a little bit. Roughly speaking, you can think of phi as having, let's say, the value 1 near the vertices that are supported by mu and 0 near the vertices supported by nu, right? Or any translation of those values, 1/2, -1/2, something like that. If phi, sort of satisfies those constraints, and you can make that precise if you would like, you will end up with a vector phi that's in this feasibility region. So this can be understood as a weaker version of this extension problem up here on the top half of the slide. So in this setting, if you apply a mean centering of the argmin f tilde, just mean center it, then you can look at the sign vector as class predictions, in your graph. So this method appears performant in quite a few settings. There are still a lot of open questions on the theory side here. I will revisit now an image that I showed you at the beginning of the talk, which is built on, once again, this sklearn digits data set. So I'm gonna take a little bit more time now to explain this image in the context of the semi-supervised learning model I just described for you. So in this image, I have a node associated to each of the examples in the sklearn digits data set. As I mentioned earlier, this has about 2,000 examples. So you're looking at about 2,000 nodes right here. The labeled nodes, the ones that were had their class information available at training time, are denoted on your screen using the images themselves. So everywhere you see a 6 here indicates an example in the data set that was labeled at training time. Similarly, there's some 2s down here, some 0s over here, and maybe I think the ones I think are kind of a difficult class. They tend to be sort of scattered throughout. Some 3s and some 9s and so on. So as you can see here, the proportion of labeled data to the size of the overall data set is relatively small. I think in this case, I was using maybe 5 or 10% of the overall data was labeled and available at the time that we trained. So in this example, what we did was we just looked at the Euclidean distance between the raw features of the images, maybe after some scaling, some global scaling according to the overall scale of the features. We just looked at the Euclidean distance. And then we drew edges if the Euclidean distance is sufficiently small. So we used a nearest neighbor pipeline here with about, I think, like maybe like log n number of nearest neighbors. So something around the order of 20 or something like that. And this creates a connected graph. And in this setting, what I'm going to do is I'm going to try and build a classifier that that predicts the labels of the images. And what you're looking at here is the setting where I have identified one measure consisting of all of the training examples that had labels available for the digit 6. So all of the 6s appear as one measure after applying a sum normalization. And then what I'm going to do is I'm going to take the measure new corresponding to everything else. So it's going to be a one versus all program here. I'm going to try and isolate one class from everything else. And this is how we sort of scale up from the binary setting to the multi-class setting. But for now, we can just think about it as a 6 or not a 6, right? If you want to think about it as a binary program. In this setting, the optimal potential here in the p equals 2, or excuse me, in the p equals 1 regime can be realized as a edge flow in an optimal transportation program. We have that interpretation because of our connection to the Beckman program through gauge duality. So I can render here the gradients of this optimal potential f tilde in our program as an edge flow. And where the gradients of the potential are very high, you see red edges. And so this allows us to connect, at least at an intuitive level, our method to a min-cut program. What I'm essentially doing is trying to draw a box or create a cut around my 6s, isolate them from the rest of the graph, and then build a prediction rule based on that. And that's roughly how this method operates. Okay, so at the end, this sort of concludes the research part of my talk. Here at the end of the talk, I just want to acknowledge my collaborators, who include Alex Cloninger, Gal Mishna, Dhruv Kohli, Xingqiao Wan, and Chester Holtz. Yeah, I also want to acknowledge the Data Science Institute here at UCSD for their support over the years, as well as, of course, Department of Mathematics and the School of Physical Sciences here at UCSD. So yeah, having acknowledged all of my amazing collaborators, I'll now turn to questions, if anybody has any.
All right, but first, let's thank the speaker by pressing some buttons. All righty, yeah. Questions for Sawyer?